Hello everyone, welcome to Technologies Discussion Channel. Today, I'd like to continue the discussion on digital modulation. Okay, so for this video, I'm going to do a deep dive on QAM's explanation. So basically this video, I will explain how quadratic amplitude modulation actually work with example, okay, so that you understand all this digital modulation. Guys, if you're keen to know more about digital modulation, please take a look on the playlist under the description. Over there, you will be able to find a series of discussion on digital modulation. This is my email. If you have any question regards on this discussion, okay, please drop me an email. Okay, or if not, if you want to have a faster response, you are always welcome to ask me your question through the comment. Before I continue, okay, I'd like to urge you guys to help this channel by like this video. For those who are new to this channel, please consider to subscribe and turn on your notification bell. Once again, thank you so much for strong support. On my previous video discussion, I have explained that the biggest motivation to put more points onto the constellation will be a better throughput. Okay, so basically this is what we want. If we are able to put more points onto the constellation diagram, okay, this will increase the throughput or the data speed. Okay, so therefore, okay, you can see that at this point, 32 PSK, it is almost very difficult to distinguish the points. So the biggest issue of PSK is also because of noise immunity. We are not able to put more points, okay, onto the PSK anymore. So in order to resolve this, okay, so later on you will see that we have a few methods. Okay, but let's quickly take a look on this 16 PSK. So basically for PSK, you can see that all these points here, 16 of them, they have a unique phase shift. Okay, so by having a unique phase shift, I will be able to identify their location. Now, because of they are very close space together, so therefore we have another method which is called the 16 APSK. A for amplitude, P for phase. Okay, so this 16 APSK, okay, like I mentioned that A for amplitude, P for phase shift keying is basically a digital modulation scheme that basically combine both amplitude and also phase modulation. From here you can see that I properly control, okay, not only my amplitude as you can see from here, 5 and 2, I also control my phase. So therefore, by properly control my amplitude and also the phase, I will be able to have this APSK configuration as my digital modulation. So there are typically two concrete rings which consist of one, okay, an inner ring with 4 or 8. Okay, so basically this is the inner ring with 4 or 8 points. Okay, so another one will be an outer ring. Okay, so basically this is actually the outer ring, okay, with 8 or 12 symbol. Okay, so the common configuration will be 4 plus 12. For this is actually we call the 8 plus 8 APSK. Okay, we have 8 in the inner and we also have 8 at the outer. So basically this is for constellation diagram for 16 APSK. Okay, you probably will ask why. Okay, so basically I put these two together. So on your left is actually the APSK and on your right is basically the 16 PSK. So from here you can see that the separation between the point will be more drastic. Okay, if we are able to control both the amplitude and also the phase. While for this 16 PSK, we only control the phase, and you can see that the spacing, okay, it will be quite difficult. Okay, if we have some noise, this may generate so-called error. So therefore, because of this, we actually prefer, okay, to be configured in this 16 APSK rather than 16 PSK. Okay, however, we also have another new types of constellation diagram, which is the 16 QAM, 16 QAM. Okay, so this quadratic amplitude modulation, okay, is a modulation techniques that transmit digital data by simultaneously vary both the amplitude and also the phase of a carrier signal. Okay, so this actually allow for higher data rate, okay, as when we compare to using only the amplitude or phase modulation. Okay, so because of this, this actually made them more efficient use of bandwidth. Okay, so basically this diagram here shows the 16 QAM. So from here, you can see that, okay, I will have a better so-called spacing between the node as compared to the 16 APSK or even 16 PSK. So basically they are all having so-called 16 level, but over here this is actually much more attractive, as you can see that the spacing is further away from point to point. Okay, so basically this is 16 QAM. As I mentioned earlier on, there is always a strong motivation, okay, to increase the level. So besides 16, okay, you can see that we also have 64 QAM, okay, which is shown over here. And we also have the latest state of art, which is the 4096 QAM. Okay, so it is so many dots that I can't even so-called show it very clearly to you guys. Okay, but I guess you can understand what is actually 4096 QAM. In fact, this 4096 QAM is used by Wi-Fi 7, okay, which is the state of art currently. Okay, guys, before I continue to explain the QAM, I need your strong support, okay, by like this video. When more guys actually help to like this video will have a better chances to reach up to a larger audience. So guys, help me press the like button now. If you again have learned something from this channel, and if you are new to this channel, please consider to subscribe. Okay, I really appreciate your strong support. Please also remember to turn on your notification bell. Once again, thank you so much for strong support. Let's come to the explanation of QAM. Okay, so there are many words here. Okay, but on my next few slides, I'm going to explain all these words. But let me give you some brief idea what is actually QAM. Quadratic Amplitude Modulation, okay, is a family of digital modulation methods and a related set of analog modulation technique widely used in modern telecommunication to transmit information. Okay, so basically it convert two analog message or two digital bit stream by modulating the amplitude of two carrier wave. Okay, so this modulation actually employ either amplitude shift keying for digital signal or amplitude modulation for analog signal. Okay, a lot of work, but later on I will help you to digest this. Okay, the two carrier wave actually share the same frequency, okay, but are 90-degree out of phase. So basically the carrier, they are actually 90-degree out of phase. So basically this is actually a condition they call orthogonal or quadratic. Okay, the transmit signal is formed by combining these two carrier. At the receiver, okay, their orthogonal actually allow them to be coherent separate, okay, when we actually do the demodulation. A key feature of QAM is that the modulating signal have a low frequency or bandwidth as compared to the carrier frequency. Therefore, okay, it will be a narrow band if we so-called assume this. Okay, a lot of work, but let me explain, okay, how can we actually form the QAM. Okay, so let's start. Okay, so this page here shows the 16 QAM. Okay, so for a start, I like to just focus on this 4 QAM first. Okay, so later on, I will explain to the rest of the QAM. This is, I mentioned earlier on, this is actually a 16 QAM. But for a start, let's focus on this 4 QAM first. Okay, so basically this is again is a so-called IQ diagram. Okay, so basically from here you can see that, let's say, okay, so basically Q will be controlling the lower SB. I actually will control the higher SB. What does that mean? Okay, I come to this later. So basically the lower will be the one who do first, after that followed by higher. So this is my LSB. So basically from here, you can see that the higher value will be the message 0. The lower value will be the message 1. Okay, so basically this is the point here. So basically this is a LSB, which means that I need to do this first. So when this is higher, this will be all message 0. When this is actually lower, this will be all message 1. So from here, okay, I can easily jot the first bit of data. Remember, this is all higher, so these are all message 0. This is lower, so these are all message 1. Okay, so this is one thing that I done. Okay, so I have done this configuration. So next, okay, will be the higher SB. Okay, so I'll be controlling the higher SB. Okay, again, this will be the higher SB. As you can see, the higher again will be equal to message 0. Lower will be message 1. Okay, so basically, this I will actually fill up my second bit here. So this is what I mentioned. The lower bit is actually what I obtained earlier on. Okay, this so-called higher bit 0 is actually what I'm going to obtain now. So basically, if you still remember, there's a one green color here, which means that they are all 0. And if you still remember, there's a blue color line here. So this is all 1. So basically, I have successfully done up the 4 QAM from here. Okay, so in short, you always do the lower sideband and the higher sideband. Okay, so basically on the lower sideband, okay, basically this is higher, this is lower. So the higher one, you can see that they are actually all zero. Okay, the lower sideband, and the lower one will be all message one. Okay, after that, then you do the higher sideband. Okay, so basically higher sideband, this is higher, this is all message zero, this is all message one. So therefore, these are all message zero, these are all message one. And from here, I have successfully done up the 4 QAM, which I mentioned earlier on. This is what I want to do. So next, once I have done this, what I'm going to do is basically I will do a mirror. Okay, so basically I'll do a mirror image. So this will be a mirror image, and this will be a mirror image. So I have done this two zone of 4 QAM. So next again, another mirror image on the other side here. So I will be doing another mirror image. So basically you can see from here, these are all mirror image. So basically I have done, okay, the so-called the LSB bit of all the 16 point over here. I have the lowest 2 bit I have done. So next, I'm going to do up the third bit. How can I actually do the third bit? Okay, again, this will be the lower sideband and this will be the higher sideband. How should I do this? Okay, so let's say this is a message. Okay, so basically this is a message. Since this is 16 QAM, okay, so I know that I can actually separate into 4 bits. 2 to the power of 4 is equal to 16 level. So I know that I'll be controlling 4 bits here. Okay, so from here you can imagine that, okay, this 2 bit here, okay, will be represented by the 4 QAM which I illustrate earlier on. Okay, so basically this 4 bit here will be the 4 QAM which I have illustrated earlier on. This 10, how can I actually obtain it? Let me explain this. Okay, so basically for this 10 again, okay, I'm going to focus on this lower side bit here. Okay, so these are so-called the higher point. So I will indicate a 0 inside. Okay, so basically these are what we call the lower one, which we are going to assign a message one onto the third bit here. So basically, in short, over here, okay, all these I will have a 0 in front. Okay, all these I will have a 0 in front, and all these I will have a message one in front. Okay, so therefore, I have successfully done up all this. So like I mentioned, all these I will have a 0 in front, all these, okay, all 0 in front, and all these I will have a 1 in front, as you can see from here. So I'm done up, okay, on the third bit, which is here. Okay, so basically this is why we need to do the Q first, because again, they are on the lower side band. So now I'm going to do a higher side band here. Okay, so for higher side band, okay, again, okay, the higher one will be all 0, the lower one will be all 1. So from here you can see that I will be also able to do out all the bit here. So the most so-called higher bits is basically done out. So basically all this here will have a 0 in front, all this will have a 0 in front. Okay, all this will have a 0 in front, and all this will have a 1 in front. Okay, so once I done up this, you can see that I actually have successfully done up all the 16 QAM from here. Okay, so basically from here you can see that if let's say the message is 1011, okay, basically you can see that over here, okay, will be identified by this point here, 1011. Okay, so basically this is how we actually represent the 16 QAM. Okay, by controlling, okay, basically this will be formed up by the 4 QAM. This will be basically formed up, okay, by the so-called the zone, okay, and then we have successfully represent the 16 QAM as you can see from here. Okay, so these are all the words that I mentioned earlier on, but over here, one thing I want to highlight is basically you can see that the the first part will be done by the APSK or the amplitude modulation. Next part will be doing up by the frequency, which are 90 degrees, so-called separate by phase. Okay, with this, okay, I would like to end my discussion. Okay, I hope with this video, you actually understand what is actually quadratic amplitude modulation. With this, thank you so much. I hope to see you guys soon. Bye for now. Thank you so much.